Okay, thank you for the introduction. So before getting started, I just want to thank the event and committee members because I really appreciate putting on this event, and it's been great seeing everyone's talk today. And I appreciate everyone staying to see my talk at the end of the day too. I know some of us are in Australia where it's extremely late. So thank you to everyone, and I appreciate being here. Okay, so today I'll be talking about ways to accelerate variance-reduced stochastic gradient methods. And I think this work affects a lot of different optimization methods and touches on a lot of different applications. So I hope throughout this talk, I touch on something that is relevant to your research as well. So the class of problems that I'll be considering in the talk today are optimization problems that can be decomposed into the sum of two functions. So we have a smooth part to the objective, which is the sum of n L Lipschitz continuously differentiable functions. And then we also have a non-smooth component to the objective that doesn't have to be differentiable, but it does have to be simple in a way that I'll define later on. And so we don't impose convexity for the whole talk on any of these functions, but it will be relevant to some of our results, and I'll highlight that when it comes up. So the reason I'm considering this class of problems is because a lot of different applications give rise to problems that can be put into this class. So a huge example that people use all over the world every day is a lasso regression. So if you have a regression problem and you want to add in an L1 norm for regularization, and I'll show an example later on. This is the lasso problem, and it's very popular in machine learning and statistics. And there are many other examples that fit into this problem class as well. So non-negative PCA, this is actually a non-convex problem where the f sub i's are L2 norms with some sort of affine operator within the norm. You can also choose Fi to be a Kullback-Leibler divergence, which is important in a lot of statistical applications. And for problems like image reconstruction or image denoising, you can take the non-smooth part to be the total variation pseudonorm. So this class of problems encompasses a lot of different applications, so it's very useful to study. And you can even encode constraints in this non-smooth function g by letting it be the indicator function of a convex set. So it's a problem structure, it's very rich, and it applies to a lot of different applications. Okay, and throughout this talk, I'll be looking at an application in particular for visualization, and this is the lasso regression problem. So in this problem, we're trying to minimize x. We're trying to minimize this objective function in x, where we have an L2 loss term, and we take the expectation of this loss over the choice of some training data set. So some features W and some labels Y. And we also tack on this L1 regularizer that will give us a more biased solution that's more stable to unseen data. And you see this fits into our problem structure because we have this finite sum here of smooth functions, and we have this non-smooth regularizer. So it's perfect for us to visualize for our problem class. And this is what the loss landscape looks like for the lasso problem. So we get these ellipses from the L2 norm, and then we have this non-differentiable part around where W is, or where X is equal to 0. And that comes from the L1 norm here. So it's a complex loss landscape, mainly because of this non-differentiable kink in the ellipses here. Okay, and we know how to solve problems like these already. So if we don't have the non-smooth component, this is just a least squares problem, and we can solve this in many different ways, but I'll show what gradient descent looks like. So the algorithm gradient descent just moves in the direction of the negative gradient with some step size predetermined until you reach convergence and at the optimum. And gradient descent is useful because it's safe, but it's also kind of boring. So every single iteration, we're guaranteed to decrease the objective, and we do this until we reach the minimum. And it's nice and safe, but also slow and kind of boring. And this is the solution that we get with gradient descent. We get a nice line of best fit. And of course, we ignored the non-smooth component there. So now I want to add it back in. And the reason we add in this L1 regularizer here is because in some applications, it can help us be robust to outliers. So in the last example, we had no outliers, but if we add in these outliers here, the least squares solution starts to be affected by these few but huge outliers. And the lasso solution is less affected. So that's why we're involving this non-smooth component at all. We can get better fits to data in a lot of cases. And so this problem we can also solve using a variant of gradient descent called proximal gradient descent. And in proximal gradient descent, we take this regular gradient descent step, and then we perform soft thresholding or a shrinkage operator. And what this does is it makes the weights somewhat smaller at every iteration by a factor proportional to the step size. And so we're still guaranteed to converge now to the solution of the non-smooth problem. And this requires no extra computation per iteration. So we've effectively solved this non-smooth problem. Okay, so we have this class of problems, sum of smooth functions, and then a non-smooth part. And we can solve it using proximal gradient descent. So the gradient descent part solves the non-smooth or the smooth part of the objective. And this prox term, which is defined below more generally than for the L1 norm, that solves the non-smooth part. Okay, so the issue though is in today's applications, this n here is huge. It's on the order of hundreds of millions or even billions for a lot of applications. Usually it's proportional to the size of your training data. And so we have a lot of training data in today's applications. And proximal gradient descent, although it solves this problem, it requires the full gradient of each of these components every iteration, which is really expensive to compute. And so we want a way to get around this huge amount of computation that we have to do every iteration for proximal gradient descent. And we would like to preserve all of the nice behaviors of proximal gradient descent with a resulting algorithm. Okay, so researchers now have turned to stochastic gradient methods to get around this large N problem. So stochastic gradient methods take a subset of those indices of f sub i's, and they use a stochastic estimate of the gradient to replace the gradient. So for example, the Sgd estimator just takes a small random sample of those indices, computes the gradient, and then uses their mean to replace the full gradient. So it's a really simple approach. And there are more complex approaches as well. So I've also included the Saga gradient estimator and the SVRG gradient estimators. And these two estimators are known as variance-reduced estimators because they have smaller variance in general than the Sgd estimator. And the way that they can achieve this is by using gradient histories. So the Saga gradient estimator keeps the mean of a running table of gradients. And every time you compute a new gradient for an index, you replace that in the table. And SVRG does a similar procedure. So very infrequently, maybe every n iterations, you compute the full gradient at some anchor point, x tilde. And then you use this full gradient for future gradient estimates. And so by incorporating gradient history, we can reduce the variance of these gradient estimators, and we can get better performing algorithms. So Saga and SVRG are known as variance-reduced estimators, where the Sgd estimator is not variance-reduced. All right, and now we're going to talk about convergence rates, because this is how we compare the quality of different algorithms. So proximal gradient descent on convex problems, when the f sub I and g are convex, it decreases the suboptimality like 1 over k. And for variance-reduced algorithms like SVRG and Saga, we get the same convergence rate in expectation. And this is a really exciting result because we're doing much less computation per iteration and achieving roughly the same convergence rate. So when Saga and SVRG were developed, these were big results. They're saving a lot of computation for many different applications. So this is a really remarkable achievement. And if The function, moreover, is strongly convex. So if we can lower bound our objective function by mu times some quadratic function, then we can get a linear convergence rate. So we converge like 1 over rho, where rho is 1 plus mu over L, and this quantity mu over L is the condition number of our objective. So the more poorly an objective is conditioned, the slower this linear rate of convergence is. Okay, and Saga and SVRG attain similar convergence rates, but in expectation again. Okay, so there's still one gaping hole in the study of stochastic gradient methods, and that is that the convergence rates we've talked about before are suboptimal. So Nesterov, several decades ago, introduced a momentum trick that turns gradient descent or proximal gradient descent into a multi-step method, and it favors iterates that move in the same direction as the previous iterations. And this momentum that Nesterov added to proximal gradient descent significantly improves the convergence rate of the algorithm. So in the convex case, instead of 1 over k, we get 1 over k squared. And in the strongly convex case, we get a linear convergence rate that depends on the square root of the condition number. And these improvements are huge, and they cost no extra computation at each iteration. And just to see how huge these improvements are, let's look at a small bit of momentum added to proximal gradient descent, and we converge much faster than without any momentum. And of course, there is a catch, and the catch is that momentum sacrifices stability for speed. So gradient descent is the safe and boring option, and it decreases the objective value every iteration, and we get this nice smooth convergence to the optimum. But with momentum, we don't guarantee that the objective decreases, and we actually move away from the optimum every once in a while. So we get this bouncing behavior. And to see what that looks like in practice, we can increase the momentum parameter. And you see it gets a little bit more unstable, but we're still converging faster than gradient descent. And if we use a large momentum, then we're bouncing all over the optimum, but we can still converge in the limit, and we're still faster than gradient descent. So we're losing stability, but in the full gradient case, it doesn't really matter. When we have access to the full gradients, we're still converging to the gradient descent solution in the end. And now we want to figure out if this can be extended to stochastic gradient methods. So when we add momentum, we lose some stability. And when we use a stochastic gradient rather than the full gradient, we also lose stability. And so it makes sense that these two methods might not be able to be combined because the instabilities would compound and we wouldn't even get a convergent algorithm. And to see this, let's look at the Sgd estimator with momentum. So after many iterations, we get huge variance in the iterates, much more than we see with Sgd without momentum. So the instability of momentum is propagating bad information each iteration when you use a stochastic gradient. And here's this comparison of the solutions. So Sgd without momentum, it finds a better solution than Sgd with momentum. Okay, so this is sort of a downer result. It's sort of disappointing because accelerated gradient methods really are much better than unaccelerated methods. And it appears that we can't just naively extend it to stochastic gradient methods. So in the stochastic setting, if we get a bad gradient estimate, momentum propagates that information for all future iterations, which can cause the method to not converge or to have even higher variance than it should. And so one way to get around this that was recently discovered is to use a negative momentum technique. So Katyusha is an algorithm based on SVRG, which we discussed before, that incorporates negative momentum. And this negative momentum draws the iterates toward the anchor point where we know the full gradient. So if you recall for SVRG, we compute the full gradient not very often, every n iterations maybe. And so this negative momentum halts our progress and brings it toward this anchor point so that we have more stability and momentum can have the desired effect. So this is a great achievement, figuring out that this negative momentum introduces stability to stochastic methods. But there are also a lot of problems with negative momentum. So most importantly, it sort of skirts our poor understanding of accelerated stochastic methods. So the real question is there a way we can use momentum with stochastic algorithms? And this sort of changes the stochastic algorithms to work with momentum, to give them more stability so that we can use momentum. And this sort of, it doesn't answer the original question, it skirts around it. Also, it's unclear if it's even necessary to use negative momentum, and this is acknowledged by the author of the Katiusha algorithm. So this author states, sometimes Nesterov's momentum indeed makes stochastic methods faster with careful parameter tuning. Okay, so there's still this quality that we don't understand of accelerated stochastic gradient methods. So sometimes they work, sometimes they don't. And as researchers, we would like to understand why this is true. Also, Nesterov's trick can accelerate many different first-order algorithms, but Katiusha momentum, negative momentum, only works with SVRG, because SVRG is the only algorithm that computes this anchor point that can be used for negative momentum. And so it'd be nice to find a more general approach to acceleration that can accelerate a lot of stochastic gradient methods. And also, without careful parameter tuning, negative momentum can perform worse than non-accelerated SVRG. And this is because we're introducing too much stability. We're halting progress so that we're stable too much. And so this can hold us back in practice. Okay, and to illustrate some of these points, I want to show what SVRG looks like with momentum and without any negative momentum. So we can see SVRG with momentum has already converged, and SVRG without momentum is still bouncing around. And we see this with the objective plots as well. So adding momentum to SVRG appears to work in certain scenarios. And the question that we would like to answer as researchers is, what are these scenarios? And can we design a generalizable approach to acceleration around this observation? Okay, and that is what our results do. So these are the questions that our results answer. So we use a linear coupling acceleration, which is a reinterpretation of Nesterov's momentum, to design a general approach to accelerating stochastic gradient methods. And so this is what our algorithm looks like. It looks like proximal gradient descent with two other auxiliary sequences that provide the momentum to the approach. And I'll go into more details about this algorithm later because there are a lot of details that are required to get it to work with stochastic gradient methods. So this acceleration technique works for many different stochastic gradient methods, and it achieves optimal convergence rates, just like in the full gradient case, up to a constant that depends on the mean squared error of the estimator that you use. And I'll go into that in more detail for specific estimators later on. Okay, so here are some more details on our momentum scheme. So as the author of Katiusha noticed, parameter tuning matters. So when you're accelerating stochastic gradient methods using our approach, you want to use a small step size that increases as the algorithm converges. And you also want to use a momentum parameter that's very aggressive, but gets more aggressive as you converge as well. And we specify exactly what these parameters should be throughout the algorithm. So this isn't up to guesswork by the person implementing the method. We give theoretical suggestions on these parameter settings. And also, these values should increase with smaller mean squared error in the gradient estimator. So it doesn't matter what gradient estimator you use, but if the mean squared error is small, you should use a larger step size, and you should use less aggressive momentum. Okay, so those were the parameter setting tricks that we discovered that allowed us to achieve our results. But then we also needed a new proof technique to prove these results. And so we call this proof technique using a non-Markovian Lyapunov functional. So usually in optimization, you define some sort of Lyapunov functional that's a non-negative quantity like the suboptimality or the distance to the solution. And you show that this decreases every iteration. And then you're guaranteed to have convergence, and you can get an idea of how fast you converge by how much you decrease every iteration. So this does not work with stochastic methods that also have momentum. You're not guaranteed to have decrease of a Lyapunov functional every iteration. So you have to consider all iterations at once, which is where this non-Markovian property of this Lyapunov functional comes into play. So we show that for a lot of different gradient estimators, you can upper bound the mean squared error by some sequence that can be decomposed into a geometrically decaying part, and then this non-Markovian part, where you have to consider all past iterations. But you can bound this by a usable quantity. Okay, and to our knowledge, we cannot use a single iteration Lyapunov functional, which is what the majority of the optimization literature uses. So this is a new technique that seems to be powerful in this setting. And these are the rates that we prove for our accelerated methods. So we can use our methods to accelerate Saga and SVRG, as well as some other gradient estimators. And we get an n squared dependence and a 1 over k squared dependence in the convex case. In strongly convex cases, we have linear convergence with a square root dependence on the condition number. And we have an n to the 2/3 dependence in the strongly convex case for the linear rate. So while full gradient descent has a linear dependence in n, we have an n to the 2/3 dependence, which represents huge savings over full gradient methods. Okay, and we achieve the same optimal convergence rates as accelerated proximal gradient descent. So these rates can actually be improved. So it was recently shown that the optimal dependence on n in the strongly convex case is square root n, and we have n to the 2/3. So we have the optimal dependence on the number of iterations, so with the square root of the condition number and the square of the number of iterations, but we haven't met the optimal dependence on n. And to do this, we conjecture that we need a stochastic gradient estimator with a smaller mean squared error. Okay, but so far it's very nice. We have an acceleration scheme that can accelerate all sorts of stochastic gradient methods, not just one method. And the only difference in the rates depends on the MSE of the gradient estimator that you use. And now I'm going to try to achieve the optimal dependence on n, a square root dependence on n. And I'll do this by looking at other types of gradient estimators, so in particular biased estimators. And I'll show that they have nice properties that might allow us to achieve this optimal dependence on n. So all of the gradient estimators we've considered so far, like Saga and SVRG, they are unbiased. So their expectation is equal to the full gradient. And there are some other estimators that have been studied in the literature that are biased, so they don't have this property. Like SAG or SAG, for example, is like Saga, but it has a different coefficient multiplying the gradient that you compute each iteration, and that makes it biased. And there's also the Sarah estimator, which is like SVRG. So every n iterations, you compute the full gradient, and then you use past gradient estimates to inform the current gradient estimate. And both of these estimators are biased. And the reason biased estimators aren't as popular as unbiased ones is because they're much harder to study. So before our work, there was no proximal support for these biased estimators, which means they only work when g is equal to 0. So the objective is differentiable. The convergence proofs are notoriously complex. So for example, the convergence proof of SAG required computational verification of a certain step. And while that's fine, it sort of skirts our understanding of these biased estimators as well. So as a mathematician, I would like to have a general approach to these biased estimators so we could prove convergence rates without the need for computational verification. And also, biased estimators usually admit suboptimal convergence rates. And they're suboptimal in a very small sense. So Sarah converges like 1 over k, or log 1 over k, compared to 1 over k. Okay, so if we want to incorporate biased estimators into our acceleration framework, first we need a whole new framework just to study the convergence of these biased estimators. So that's where we started. And you also might wonder, what are even the benefits of bias? Why would we study these if they're so difficult to work with? And so recent work has shown that the Sarah estimator, for example, is the best possible estimator you can use in non-convex optimization. So it achieves the Oracle complexity lower bound for non-convex problems. And this lower bound is square root n over k rather than n over k for other stochastic gradient methods. And so we see this square root n dependence in the result, which gives us hope that Sarah could do the same for our accelerated methods as well. Okay, and we also see in practice, biased gradient methods can often significantly outperform unbiased methods. So here the black line is unbiased Saga, and we can introduce bias with this tuning parameter theta, and we get better performance with certain types of bias. So biased estimators are definitely worth studying, even though it's difficult to study them. Okay, so to develop a framework for studying these bias gradient estimators, we wanted to understand the bias variance trade-off in these estimators. And so the classical bias variance trade-off says that you can decompose the mean squared error of any estimator into the variance term and a squared bias term. And the idea of this trade-off is you can introduce bias, and if it lowers the variance, then you might get a better estimate in terms of the mean squared error. So this is a bias variance trade-off. And we wanted to understand what that looked like for bias gradient estimators in optimization. And so this is where we started developing our framework. And we said, we found that the optimal stochastic gradient estimator minimizes this quantity, which is a bias variance trade-off. We have this inner product bias term that disappears when the estimator is unbiased, together with the mean squared error of the estimator. And so what this relationship says is if we can minimize the sum of these two terms, we have an optimal estimator. So this is the bias variance trade-off in optimization. And it also captures the fact that the gradient isn't always the best direction to use in optimization. There exist better directions. So namely, if our estimator is biased toward the solution, then we get a better method. And of course, you can't know that a priori, but that fact is captured in our bias variance trade-off for stochastic gradient methods. Okay, so using this stochastic gradient method bias variance trade-off, we can show that for the Sarah estimator, both of these terms are bounded above by order n, while for Saga and SVRG, the mean squared error is order n squared, and the bias, of course, is 0. So because these two terms are equal, we can assume that they're roughly optimal. So using the Sarah estimator roughly optimizes this bias variance trade-off. And this is why we get better convergence rates for the Sarah gradient estimator. Okay, so using this framework we developed for studying bias gradient methods, we can prove improved convergence rates for algorithms like Sarah. So we get classical convergence rates with a square root n dependence. And this was the square root n dependence we're looking for our accelerated methods. And we also recover the result that in the non-convex case, we get the Oracle complexity lower bound for Sarah. So our framework is powerful for these methods, and it allows us to prove new results and recover the best existing results as well. And because we have a framework, we can use it to study new stochastic gradient methods. So we did this. We introduced a stochastic gradient method called Sarge, or stochastic average recursive gradient. That's sort of like Saga. So as Sarah is like SVRG, Sarge is like Saga in that it keeps a table of previous gradient estimates, but it uses bias to improve the performance of the algorithm. So it's like Saga, but biased. And it's better than Sarah because it requires computing the full gradient only once upon initialization, whereas Sarah needs a full gradient every 2n iterations or so, just like SVRG. Okay, and just to give a few more useful properties of this Sarge gradient estimator that we introduced, the bias in Sarge decreases geometrically, just like its mean squared error. So when we're near convergence, Sarge has a very small mean squared error and also has a very small bias. And we think that this helps its performance compared to other stochastic gradient estimators. And also we can prove that Sarge achieves a square root n dependence in all of its convergence rates, and it achieves the Oracle complexity lower bound for non-convex optimization, just like Sarah, but it never requires the full gradient after initialization, whereas Sarah requires the full gradient every 2n or so iterations. Okay, so we now have a way of studying stochastic or biased stochastic gradient methods, and we can use this to develop new biased algorithms. And then a natural question is, can we combine our acceleration framework with our framework to study biased estimators? And can this help us close the gap on the square root n dependence for our accelerated convergence rates? And so in this plot, I show Sarah with momentum and Sarah without momentum using our acceleration scheme. And we see it exhibits kind of odd behavior. So Sarah, it often plateaus and then makes huge jumps in convergence when you compute the full gradient. And the way it does this, you can also see it in this suboptimality plot. But because it does this, it often fights with the momentum that we add to it. And so you can see right here, especially, this is generally in a full gradient method where you would see non-convergence. So you would see the iterates move away from the optimum. And when that happens with Sarah, you lose one of the jumps and you plateau at a higher objective value. And so bias seems to kind of fight with our acceleration framework in some cases. And we still prove accelerated convergence rates for Sarah and for Sarge when we apply our acceleration framework, but we don't achieve the square root n dependence yet. And so this is where future work is taking me. So I want to understand if there's a better way to incorporate acceleration into these biased methods so that we get even better convergence rates. All right, and so I'm going to finish up by showing you a lot more examples. So we've been looking at Lasso throughout this talk, but let's look at Lasso and compare all of these different algorithms using a Lasso problem. So all the dotted lines here are accelerated methods that match with the same colored line elsewhere in the plot. And so we can see, especially on the largest problems, acceleration can offer huge performance benefits for Saga and SVRG, and slightly smaller performance benefits for biased algorithms like Sarge and Sarah. Okay, and one other thing I want to point out is the pink line here is Katyusha. So Katyusha is the algorithm that uses negative momentum. And if we use a theoretically optimal parameter setting of 1/2 for the negative momentum parameter, we get much worse performance than non-accelerated algorithms. And then if we take away negative momentum completely, set tau2 equal to 0, then we get performance that matches accelerated schemes using our framework. And in fact, when Katyusha has no negative momentum, it resembles SVRG without any, or with acceleration using our acceleration framework. So we can see negative momentum maybe has its place, but it's definitely not necessary to achieve acceleration with these algorithms. Okay, and I also want to show this for ridge regression. So this is the same as the lasso problem, but without L1 regularization and with L2 regularization. And we get a similar story. So acceleration significantly improves Saga and SVRG, especially when there's large data. And it also improves Sarah and Sarge, but perhaps to a lesser extent. And those are the two bias methods. Okay, and alluding to future work a little bit, I want to talk about its performance on non-convex problems. So we talked a lot about non-convex problems when we were looking at biased algorithms, and we showed that biased algorithms often achieve the Oracle complexity lower bound for these problems. And we see that biased methods do tend to perform better on this non-convex problem. And one thing that we're investigating right now is if stochasticity combined with non-convexity can help find better local optima. So in non-convex problems, there's a huge range of quality in the solutions that you'll end up with. And we think that maybe with stochastic gradient methods, you can hop out of local optima and find better solutions. And it would also be interesting to consider adding momentum because this has also been shown to have the same effect to hop out of poor local optima and find good solutions. So that's a good direction for future work. Okay, so takeaways from this talk. I don't want anyone to be afraid of using momentum with variance-reduced stochastic optimization, especially if you're using the framework that we suggest. You can do this safely so you get convergence even though it's unstable. Also, no one should be afraid to study or use bias gradient estimators. So bias can often lower an estimator's mean squared error, navigate the bias variance trade-off that we investigated for optimization methods, and improve performance of optimization algorithms. And in future work, I plan to look at the combined effects of bias and momentum, as well as momentum dynamics in the non-convex setting, and combining that with stochasticity. And before concluding, I want to talk about some other applications of our results as well. So our non-Markovian Lyapunov analysis that we use in our acceleration approach has also been used to study variance reduction in Hamiltonian Monte Carlo methods, and bias gradient estimators such as Sarge are now also used in HMC methods. And lastly, one thing that I found very interesting is another group has used similar proof techniques to show that accelerated stochastic gradient descent with some sophistication can outperform non-accelerated SGD, which is interesting because SGD is not variance reduced. And in our example, we showed accelerated SGD was much worse. Okay, so finally, thank you very much to the prize committee members and the event organizers for putting on this event. It's been great seeing everyone's talk throughout the day, and I'm happy to answer any questions that you might have.
Okay, thank you very much, Derek, for a great talk. I have a question. When you were introducing the non-Markovian Lyapunov functionals, I understand that's a really useful tool for theoretical work. Is there any hope of using that as a practical tool to monitor convergence, or is it too expensive to evaluate and store?
Yeah, that's a really good question. It is too expensive to evaluate. Let me just go back to the slide. So it's too expensive to use as a convergence criterion, for example, just because you'd have to store all sorts of iterates and gradients as the algorithm converges. But one thing I have considered is using some sort of running tally of this quantity here to inform step sizes or something like this. And so if this upper bounds the mean squared error of the estimator. So if it's small, maybe we can increase the step size more than theory would suggest. So that's one thing I've considered.
Okay, great. Des, you have a question?
Yes, thank you, Derek. Just regarding the slides at the end, you had the norm of f of x k minus f of x star. just to clarify, it might be a different X star in each of those plots, is that in each curve? Yeah.
That's true, yes. In the convex setting, it might be that you have multiple solutions. And so the X star could depend on the stochasticity in the algorithm and the initial starting point.
So if I was just concerned with the size of F, would that be a different question?
Oh, in the convex case, no, it wouldn't, because while you don't have strong convergence, you still have weak convergence. So there's a single minimum, even though there might be multiple minimizers.
Yeah.
Yeah.
But does the analysis tell me that the size of F itself goes down at a certain rate, or is that just a different type of question?
Let's see, are you referring to this F
or
or
the objective function?
the objective function? So in the analysis of full gradient methods, the objective function itself does decrease every iteration.
Yeah.
Yeah.
Okay, thanks.
Okay, so next it was Nick Gould on the Q&A. He says, great talk. Do your methods typically behave like their worst case bounds, or is this exceptional, i.e. the algorithms usually behave much better?
That's a great question. And the algorithms usually behave better than our worst case bounds. For example, step sizes that depend inversely on n, those are usually pessimistic step sizes. You can usually use larger step sizes. And so the difference in the size of the step sizes you can use is huge compared to theory and practice, but the performance of the method isn't that different in theory and in practice, but you do see a difference. Usually you perform better than the worst case bounds.
Great. Lyndon Roberts is next.
Yeah. Yeah. Hi, Derek. Thanks for the talk. My question was, I guess it's related, is a lot of these methods, there's a lot of sensitivity around tuning things like learning rates and hyperparameters. How robust is what you have compared to what's out there?
How robust? That's a great question. So if you use the parameter settings suggested by our theory, you'll get better performance than non-accelerated methods. But if you stray from our theoretical suggestions, then there does seem to be a lot of difference in what you can get in terms of performance. So yeah, when you stray from using the step sizes that we suggest, you can get worse performance than non-accelerated methods. Yeah.
Okay.
So the methods are very sensitive to the step size and to the momentum parameter, slightly less than the step size, but it's sensitive to both.
Okay, thanks.
Okay, and Andre Sully also asked a question in the Q&A. He says, thanks for a nice talk. Is it an issue from a practical point of view if the functions, which you had fj, have vastly differing Lipschitz constants? Right now you have one global Lipschitz constant that you plug into your bounds. What happens if they're vastly different?
Yes, so I probably should have said this actually. The Lipschitz constant that we've been considering is the maximum Lipschitz constant for each of the f sub i's. And in general, that Lipschitz constant can be up to n times larger than the Lipschitz constant of f itself, the average of all those f sub i's. So when you see our results, in order to get an idea of the absolute worst case, you should multiply the Lipschitz constant by n. But that rarely is the case, yeah.
Okay, what about from a practical point of view though? Is that a consideration from a practical point of view?
Yeah, so for some problems, you get huge variance in the Lipschitz constants for each f sub I. So one great example is the image deblurring problem. So for a lot of deblurring kernels, I mean, each L comes from a single row of a matrix, the matrix that's in the L2 data fitting term. And you can get huge variance in those Lipschitz constants. And if you do see that, then stochastic methods are less effective. And so in the extreme, it would be better to use a full gradient method than a stochastic method if you have huge differences in the Lipschitz constants between the f sub i's. Yeah. So in practice, sometimes it's a problem, like with image deblurring, but even in that case, it makes sense to use stochastic methods most of the time.
Okay, I think that's it for questions. So thank you again, Derek, and thank you to all the participants today.